All right, Physical Organic Chemistry, ch7.2.7-TST-exceptions. This lecture is discussing issues from chapter 7.2.7, that is, exceptions to the transition state theory. This goes along with the selectivity that we just discussed in sections 2.4 and 2.5. Okay, we had these kinetically controlled reactions where we're looking at differences in energy in the transition states to provide insight into the energy differences based on the product distribution. Now, there's an assumption that goes along with this, and that is that for the intermediate, all of the internal energies are at equilibrium. And if we're considering, say, something like T-butyl chloride dissociating to produce a T-butyl carbocation plus chloride in a solvent-separated pair, this is fully equilibrated before the nucleophile comes in. Okay. Oops, wrong product. To give us the nucleophile there. Now, that full equilibration has a consequence. It is that if we have a chiral center and go through an SN1 reaction, it will result in racemization. Okay, it'll result in racemization, because then the nucleophile can approach either side of the planar carbocation. Okay, but what if it's not fully equilibrated? And there is connections in your textbook on page 374, and many of these exceptions to transition state theory come to us actually because of the work of Barry Carpenter at Cornell University. He's essentially made a career out of it. So let me walk you through this slide. Again, this is on page 474. It's transition state theory exceptions. So if we consider this intermediate the starting material I, the diazo compound, if it is activated to eliminate N2 and you get carbon-nitrogen bond scission to produce intermediate 4, it can then lose nitrogen and produce diradical 5. If diradical 5 has the time to fully equilibrate its internal energies, motions, and vibrations, then you would expect that the two products, the one where the cyclopropane that is formed is cis to the deuterium, to be in about a 1-to-1 ratio to where the cyclopropane is trans to the deuterium. You would not expect a deuterium isotope effect, and we're going to cover that later on in chapter 8, this far away from those two reacting centers. But when this reaction is carried out in the gas phase, it was discovered that the ratio of 3-to-2, intermediate 3 to intermediate 2, was actually a 3-to-1 ratio. Now what that suggests is that this intermediate is not fully equilibrated. So how is this happening and what does it mean? This is illustrated for us below. Okay, so the first carbon-nitrogen bond breaks, so here's our intermediate 4 again. But the loss of nitrogen, okay, that is this bond fragmenting, occurs in concert with the vibrational motion, the normal mode vibrational motion, actually, of that methylene group actually bending down. That's what this colored arrow is to indicate here. So this CH2 group is moving toward the nitrogen as the carbon-nitrogen bond breaks. And so it then has a trajectory to continue beyond the planar point and on down, and then the carbon-carbon bond forms. And of course, once the carbon-carbon bond has formed, we're kinetically stuck. And so because of the intermediate not being fully equilibrated, this intermediate that is, if that intermediate sat there and vibrated around and the CH2 group could move up and down and back and forth, again, as we pointed out above, you would expect a 1-to-1 ratio between these two species, approximately, at least very close to it. And 3-to-1 is clearly not that. And so the explanation for that, based on some very sophisticated calculations, not just the DFT things like you guys are working on in class, but what's called molecular dynamics, where they simulate many conformations and distributions of energies. Those computations are consistent with this pathway where the displacement or the loss of the nitrogen molecule is coincidental or concurrent with that CH2 normal mode vibration. Now this is basically an envelope. Right there you see the envelope conformation of the 5-membered ring, of the cyclopentane ring. Right, that envelope vibration from one side to the other, that's a normal mode vibration that we've all seen before. And so this CH2 group is swinging down as the nitrogen is displaced, and so you can imagine it has momentum that it just continues on down and results in then the formation of that bond and gives you a greater proportion of product with the stereochemistry trans, as in 3, versus as in cis for intermediate 2. All right, so that's going to conclude the discussion here. You guys be reading next time section 7.3, 7.4, and 7.5. We will continue those for next week. Hope you have a good weekend. Talk to you soon. Send me emails with any questions.